Welcome to Advanced Linear Algebra. Today, we are going to explore a fascinating and powerful concept called invariant subspaces. If you have ever wondered how mathematicians and engineers break down impossibly complex systems into manageable pieces, you are in the right place. Let us dive in and discover how certain special regions remain completely unaffected by the chaos around them. To understand our topic today, imagine you are stirring a cup of coffee with a spoon. The fluid moves all around the cup in complex, chaotic ways, mixing everything together. However, if you look at the exact center axis of the whirlpool, the liquid there only moves straight up and down, never outward. That central vertical line is a special region that stays within itself despite the chaotic stirring happening everywhere else. In linear algebra, we look for these exact kinds of stable, self-contained regions amidst complex transformations. Now that we have a mental picture, let us bring this into the world of mathematics. Suppose we have a vector space, which we will call V. We also have a linear operator denoted as T, which acts like a stirring spoon, stretching or rotating vectors. Most vectors get knocked into completely new directions. But sometimes there is a smaller, flat region inside V, called a subspace W. If applying our operator T to any vector inside W always produces an output vector that is still inside W, we call it an invariant subspace. Simply put, what happens in W stays in W. Let us look at the exact mathematical formula for this idea. The definition states that T of W belongs to W. Conceptually, this means our transformation cannot force a vector to leave its home. Here, T represents our linear operator, the rule that moves things around. The lowercase w represents any individual vector that starts inside our special subspace. The uppercase W represents the entire subspace itself. If you increase the number of vectors you test, this rule must hold true for every single one. If even one vector gets pushed outside, the subspace is not invariant. We can also write this exact same rule using set theory, which gives us a broader perspective. The formula is T of W is a subset of W. Instead of looking at one vector at a time, T of uppercase W represents the transformed version of the entire subspace all at once. The subset symbol means this new transformed shape is fully contained within the original subspace boundaries. The transformation might shrink the subspace, but it will never cause it to bulge out into the larger surrounding vector space. This allows us to study the transformation on a smaller scale. Let us visualize what this mathematical trapping looks like. On your screen, you see a three-dimensional space with a flat blue plane representing our subspace W. Notice the original vectors, the starting arrows, live entirely on this flat surface. When the transformation T is applied, the curved arrows show where these vectors end up. The critical takeaway here is that the tips of the new arrows never point up or down away from the plane. They remain completely trapped on that exact same flat surface. If even one arrow pointed off the plane, it would lose its invariant status. Before we move on, let us see this with a concrete example. Imagine our vector space is the standard two-dimensional plane. Our linear operator T acts like a mirror, reflecting any vector across the horizontal x-axis. We want to prove that the x-axis itself is an invariant subspace under this specific reflection. To do this, we must pick a generic vector that lives exactly on the x-axis. We write this as a column matrix, where the top entry is x, representing any horizontal position, and the bottom entry is exactly 0, guaranteeing it has no vertical height. Continuing with our example, we need to apply our transformation to the vector we just defined. The mathematical rule for our reflection operator T takes any general vector with coordinates x and y, leaves the horizontal x coordinate completely unchanged, and multiplies the vertical y coordinate by -1. This effectively flips the vector upside down across the horizontal axis. Now, we will apply this exact reflection rule specifically to our vector v from the x-axis, substituting our specific coordinates into the transformation function. Let us finish the calculation. We substitute our vertical coordinate, which is 0, into the rule. The rule tells us to multiply that 0 by -1. Since -0 is just 0, the output vector is exactly the same as the input vector. The resulting vector still has a vertical coordinate of 0, meaning it lives perfectly on the x-axis. Physically, this means a vector lying flat on the mirror does not move when reflected. We have successfully proven that the x-axis is an invariant subspace under this reflection. Now that we have used the definition in a simple example, let us look at a very important type of invariant subspace. Recall what an eigenvector is. It is a special vector that only gets stretched or shrunk by an operator, never rotated. The amount it stretches is called the eigenvalue, represented by lambda. If we take all possible scalar multiples of this eigenvector, we form a straight line, which is a one-dimensional subspace. We are going to prove that this subspace, spanned by an eigenvector, is always an invariant subspace. Let us begin our proof. We want to establish that the span of an eigenvector is invariant. We start by defining W as the one-dimensional subspace spanned by our eigenvector V. Next, we pick a generic vector W that lives inside this subspace W. Because W is simply the scan of V, every single vector inside it must be written as some constant number, which we will call C, multiplied by our eigenvector V. This sets up our starting point perfectly. By defining our generic vector this way, we ensure that our proof will apply to the entire line, not just a single point. Moving forward with the derivation, we apply our linear operator t to both sides of our equation. We want to see exactly what happens to our generic vector w when the transformation acts upon it. Because t is a linear operator, it has a very special property. We can pull constant numbers out to the front. The scalar c simply slides outside the transformation. This is a crucial step because it means we only need to evaluate how the operator t affects the eigenvector v itself, ignoring the scalar for a moment. This linearity is the engine that makes the entire proof work. Now for the final steps. We use the fundamental definition of an eigenvector, which tells us that t of v is simply lambda times v. We substitute this definition back into our equation. Now, instead of having the operator t, we only have regular numbers multiplying our vector. We can group the two scalars, c and lambda, together. Because the final output is just a new number multiplied by v, the output vector is still a multiple of v. This gives the final result, proving that the span of an eigenvector is always an invariant subspace. The math perfectly matches our intuition. So, we have proven that eigenspaces are invariant. This brings us to an important question. Why do we care so much about this? In the real world, engineers and physicists deal with massive, incredibly complex systems, like the vibrations of an airplane wing or the quantum states of a molecule. These are modeled by enormous matrices. Invariant subspaces act like natural fault lines in these problems. They allow us to break a massive, tangled system into smaller, completely independent pieces. For example, in robotics, they help separate stable movements from shaky ones, preventing supercomputers from being overwhelmed. Let us review the most important ideas we have covered today. First, an invariant subspace is a special, self-contained region within a larger vector space. Second, when a specific linear transformation is applied, any vector starting inside this region is guaranteed to land back inside it. We saw this mathematically as T of W is a subset of W. Finally, this property is a powerful tool because it allows us to break down and simplify incredibly complex real-world transformations. You have now mastered the foundational concept of invariant subspaces. Great job!